students, and welcome to this 12th lecture of the heat transfer course EEAQ 3235, and today we're doing a continuation of the numerical methods. And as you've noticed is that we have dealt only with nodes that are interior, whereby the analysis or the heat flow problem has been that of conduction. But supposing we have a case whereby we have, let's say, a node where we have a surface like that, and onto this surface we have, let's say, a node there, and it has some neighborhood nodes. So this is our M node. It has two neighbors and another neighbor at the back there. And supposing that there is some convective environment. So convective environment. And supposing the convective heat transfer coefficient is a H, so there will be some heat flow from this node to the environment, and that flow is by convection. So other than the heat transfer by conduction, there will be some heat transfer by convection. And our resulting equation will be minus K delta Y T Mn minus T M minus 1 comma N over delta X, that is the temperature difference between this node here and that node there, okay, and the movement is in the X direction. So the area that will be perpendicular to that flow will be the area delta Y times the thickness or the width which is going into the board or out from the board, and we'll take that as O1. So minus, because of the minus K delta X. This time we're talking about either that movement or that movement. And we said that the heat transfer by conduction between these two nodes will be shared equally, half this way and half that way. Okay, so that will be delta X over 2 T M comma N plus 1 that is the one at the top. Okay, TMN, sorry, TMN minus TM comma N plus 1 over a delta Y. Then we have minus, let us put it here, K again over 2 L delta X TMN minus TM, but this time we have comma N minus 1 over L delta Y, and that must be equal to, assuming equilibrium position, the same amount that is being convected from the phase to the environment, and that is given by the Newton's law of cooling as H delta Y, the temperature difference between the surface node Tm comma N minus, and if delta X is equals to delta Y, then we'll have minus K, because the delta X and Y will cancel out. T M comma N minus T M minus 1 comma N minus a K over 2 T M comma N minus T M comma N plus 1 minus a K over 2 T M comma N minus T M comma N minus 1, which is equals to HA, not HA, but H delta Y, but we said that delta Y is equals to delta X, so we can just put delta X T M N minus T of the surroundings. By reorganizing and putting the right terms together, you'll get T M N H delta X over K plus 2 minus H delta X T surroundings divided by K minus a half T 2T 2T M comma N plus 1 plus, this is T, there's a mistake there, 2T M minus 1 comma N plus TM N plus 1 plus TM N minus 1 and all of that is equals to 0. And note that this equation here that we've come up with is only valid for a node that is on the surface, i.e. a node that is as we have there for such a node. It is not valid for a node that is at a corner. Okay, whether it is at a corner with no convective heat transfer, or whether it is a corner node with convective heat transfer, the equation will not hold. So let us have a look at a corner node. So here now we have a corner node, and it is surrounded by two environments. That environment are there, okay, and that environment are there. So the equation will be minus k delta y over 2 t m n minus t m minus 1 comma n over delta x, that is for that node as it interacts with that node. So we have Tmn, that temperature there, minus the temperature there, which is Tm minus 1 comma n, and the movement is in the x direction, okay, and the area that will be perpendicular to that motion will be delta y times 1. And we've said that the heat from this node will be divided equally between that node and that node. So a half will go this way and a half will go that way. That's why we have that 2 there. And then we have minus k delta x over 2 t mn minus tm comma n minus 1 divided by delta y. Okay, that is for this node now here. So we have, for this node interacting with this, so the temperature there, Tmn, minus the temperature there. The movement is in the y direction, and the area perpendicular to that motion definitely will be delta x at times 1, and it is a half because a half has gone the other way. And that is equals to h delta x over 2 tmn minus T surrounding, and we'll have another heat transfer by convection of H delta Y over 2 TMN minus T finite. Now again, if delta X is equals to delta Y, our equation will reduce to T M comma N H delta X over K plus 1 minus 2 H delta X T surroundings over K minus T M minus 1 comma N plus T M comma N minus 1, and that will be equal to 0. So now let's have a look at an example, and the example is derive the nodal equation for the element shown. So we have a node there that is in direct interaction with that node, a node there, a node there, and a node there. So we are after the temperature distribution around this node, and we have that surface being insulated, and there is a convective environment there. So we'll say that the conducting surfaces are AB, BC, DE, and AE. Okay, and then there will be the convecting surface is, okay, it will be a D, surface D, and our node MN. So this means that we'll have an equation T M minus 1 minus TMN over delta X delta Y K times 1. That is, if you're looking at the interaction between our node there and TM, this node here. So I've left something here, This is supposed to be comma n. So between that node there, major node and that node, and the motion is in the x direction, so the perpendicular area, that is or the area that is perpendicular to that direction is a delta y times 1, and there will be some k there. Then we'll have plus t m n plus 1 minus tmn over delta y times delta x k times 1. So here for that second term we're looking at the interaction between that node and that node there. So we have tm n plus 1 minus tmn, and the motion is in the y direction, so the area will be delta x times 1, and we're assuming an isotropic material, so k is not changing with direction, so we still have k there. And we'll have t m plus 1 comma n minus tmn t com mn, this is mn, delta x over 2, that is over 2 times k times 1. So for this one we have the interaction between that and that. And as you can see, half has gone this way, so we'll have half are going this way. And looking at that face there, okay, we are looking at that face there, so the equation will be as we have here. And then we'll have plus a tm n plus 1 minus tmn divided by delta y, and this will be a delta x, and we'll have a half k times 1. That is for that node there. We have that already. Okay, this is mn minus 1. Mn minus 1, that is for this node here interacting with that node. The motion is in the y direction, okay. And then lastly we have plus h delta y over 2 times 1 t minus t m n. So if you remove the brackets, remove the brackets, comma, assuming delta x is equals to delta y, and dividing through by k, t m minus 1 comma n minus tmn plus tm n plus 1 minus tmn plus t m plus 1 comma n over 2 minus tm n over 2 plus t m n minus 1 over 2 minus t m n over 2 plus h delta y over 2k t surroundings minus tm n, all of that is equals to 0. Then we can multiply. So this becomes 2 t m minus 1 comma n plus 2 t m n plus 1 plus t m plus 1 comma n plus t m comma n minus 1 minus t m comma n 6 tmn 6 plus h delta y over k plus h delta y over k t finite or t surroundings, which is equals to 0. So now let us have a look at example 2. That reads, the temperature distribution and the boundary conditions in a part of a solid is shown here. Determine the temperatures at the nodes marked A, B, C, and you're supposed to determine also the heat convected over the surface exposed to a convection. Okay, so let us have a look at how to go about it. So for node A, we have k times point 1. All right, because we told that, okay. Okay, there is something that I omitted. So we told that delta x is equals to 0.1, which is also equals to delta y. So we have k times 0.1, okay, so we're looking at A and this surface here, so 137 minus TA over 0.1, and the thickness is, or the width is 1. Okay, so the width is equals to 1, and we'll add to that. Now looking at that face there, 172.9 minus TA again multiplied by 0.1 over 0.1 times 1, and we have a k. All right, then we will have plus, looking at this face here, 200 minus TA divided by 0.1 times 0.1, and we have a k. Then we have plus, looking at this face here, this one here, 132.8 minus TA over 0.1 k times 0.1, and all of that is supposed to be 0. So if you simplify that, you'll get 137 plus 172.9 plus 200 plus 132.8 is equals to 4T. So, and you can solve for TA, which is equals to TA, which is equals to 160.6. So this becomes 160.7 degrees C. For B, node B, we'll have K times 0.05, because it will be a half, okay, over 0.1, 129.9 0.4 minus TB plus 103.5 minus TB divided by 0.1 K times 0.1 plus K times 0.05, and there is the last one, which is times K times 0.05 times 45.8 minus TB divided by 0.1. And that would give us 129.4 plus 2 times 103.5 plus 45.8 is equals to TB. And that gives us TB is equals to 95.6 degrees. So for C, we'll have, so now let us go finally to C. C is in direct communication with that face, that face there, and the convective environment. So between this and this, we'll have a temperature difference of 103 minus Tc. Between that and that, we'll have 67 minus Tc. And between that and that, we'll have 45.8 minus Tc. And the temperature difference there will be 30 minus Tc following that convection. So we'll have a K, and K is 1.5 times 0.05 times 45, because only a half goes to that direction, 45.8 minus Tc. That's why we have 0.05 divided by 0.1 plus 103.5 minus Tc times 0.1 times K, and K is 1.5 divided by 0.1. There is no sharing in the X direction, plus 67 minus Tc times K, and K is 1.5 times 0.05, because it is sharing between the part that is at 45.8 and the one that is at 67 degrees, divided by 0.1 plus the heat flow by convection, 30 minus Tc, times H, and H is 50, times 0.1 times 1, and that is equals to 0. So if you simplify that and solve for TC, you'll get TC is 48.7 degrees C. Now you can go ahead and calculate the heat of flow. By convection. And that will be equal 50, 200 minus 30 times 0.05 plus 50 times 0.1 0.1, 67 minus 30 plus 50 times 0.1, 48.7 minus 30 plus 50 times 0.05, 45.8 minus 30, and that gives us a figure of 743.15 watts. Thank you.